A number of concepts in mathematics and economics are based on the knowledge of special type of sets called as convex sets. Such sets have wide application in calculus and optimization. Economic concepts of preference and utility are also based on convex sets. There are numerous situations in real life when a number of variables together explain some phenomena. We often consider one factor and ignore the rest in the name of simplicity or clarity of exposure as we make the ceteris paribus assumption in economics. For a comprehensive interpretation and analysis of any observed phenomena, it is important for us to understand tools incorporating more than one variable at a time.
After studying this module, you shall be able to learn about the concept of convex sets, learn to find geometrically and algebraically whether a given set is convex or not, understand the usage of the function in the presence of two or more independent variables, evaluate limits of functions involving more than one independent variable, examine multivariate functions for continuity and differentiability. First, we will discuss about its concept and geometric illustration. A set S defined over the vector space Rn is said to be convex if for any 2 points belonging to the set, the line joining those points also belong to the set. One way of visualizing a convex set is to assume a boundary of the set. If any point of the set is visible from any other point, or if it is possible to walk through the set along a linear path without crossing the boundary, then the set is convex. Intuitively, a convex set is solid, connected, without breaks or dents in the parameter. Note that it is not mandatory for a set to be bounded for it to be convex. For example, S is equal to xy such that x square plus y square is less than 4 represents a circle of radius 2 and the boundary is not forming a part of the set, but it satisfies the definition and is convex. Consider the figures. The sets in B and D are convex while those in A and C are not, if the interior points are included in the set. If only boundary is considered as constituting the set, then none of the above set is convex. The null set and singleton sets are convex by definition. Since the hypothesis of there being 2 points is denied, the conclusion of set being convex is true by simple rules of logic. Given 2 or more convex sets, their intersection and linear combination involving additions of the positive multiples of convex sets is convex. Regular geometric shapes like circle, triangles, square, rectangle, and the like with all interior points included constitute examples of convex set. Linear inequalities also represent convex set. It may be easily verified by drawing a graph that the following are convex set. S is equal to xy such that x square plus y square plus z square is less than or equal to 4. S is equal to xy such that x is less than 0, y is greater than or equal to 0. S is equal to xy such that x is greater than equal to 0, y is greater than equal to 0, xy is greater than equal to 4. S is equal to xy such that y is greater than or equal to x square, x is greater than or equal to y square. S is equal to xy such that 3x minus 6y plus 4z is less than or equal to 4. S is equal to xy such that modulus of x plus modulus of y is less than or equal to 1. Try to draw a graph to verify that the following do not represent convex sets. S is equal to xy such that x square plus y square plus z square is greater than or equal to 4. S is equal to xy such that xy is greater than or equal to 4. S is equal to xy such that y is less than or equal to x square, x is greater than or equal to y square. S is equal to xy such that mod x plus mod y is equal to 1. S is equal to xy such that xy is less than or equal to 4. S is equal to xy such that under root x plus under root y is less than or equal to 1. Secondly, we will be discussing its definition. The geometric concept of convex set is very straightforward and is practically able to categorize given sets as convex or not convex. Its practical utility beyond 3 dimensions is, however, limited. It is meaningful to have a formal definition of a convex set that could be subjected to various algebraic manipulations. Consider two vector points P and Q in Rn and their convex or linear combination x. P is equal to P1, P2 till Pn. Q is equal to Q1, Q2 till Qn. X is equal to 1 minus lambda P plus lambda Q for all lambda belonging to the closed set 0, 1. The equation of a line segment joining the points P and Q is given by the set of all points x equal to x1, x2 till xn, satisfying x is equal to 1 minus lambda times P plus lambda Q for all lambda belonging between 0 and 1. For lambda equal to 1, x coincides with point Q, and for lambda equal to 0, x coincides with point P. For different values of lambda between 0 and 1, x represents coordinates of different points on the line between P and Q. We can now define a set S in Rn to be convex if P belonging to S, Q belonging to S, and lambda belonging to 0 and 1 implies 1 minus lambda times P plus lambda Q belonging to S. Let us now use this definition to show that S is equal to xy such that y is less than or equal to 3x represents a convex set. Let P is equal to x1 y2 and Q is equal to x2 y2 to be 2 points belonging to the given set. Then y is less than or equal to 3x1 and y2 is less than or equal to 3x2. Let set S will be convex if x belongs to S, that is, y naught is less than or equal to 3 naught. X is equal to x naught y naught, which is equal to 1 minus d x1 y1 plus lambda times x2 y2, which implies x naught is equal to 1 minus lambda times x1 plus lambda times x2 and y naught is equal to 1 minus lambda times y1 plus lambda times y2. Now we multiply 1 by 1 minus lambda and 2 by lambda and add the resulting inanities to get 1 minus lambda times y1 plus lambda times y2 is less than or equal to 1 minus lambda times 3x1 plus lambda times 3x2, which implies y naught is less than or equal to 3 naught. This proves that S is convex. Try to show using definition that a hyperplane and half space in Rn represents a convex set. Multivariate functions. A number of things in real life and environment around us typically depend on more than one factor. We normally ignore all but one factor and do the modeling. In economics, the ceteris paribus assumption does exactly the same thing. Sometimes it becomes important for us to analyze more than one factor together. In order to model them mathematically, it is important to have functions that are able to incorporate more than one independent variable. Functions of two variables. A function f of two variables, say x and y, with domain D, is a rule that assigns a unique real number fxy to each point xy belonging to D. Domain D is equal to xy such that fxy belongs to R, and range is a set of all f values. In economics, it is often crucial to be clear about the domains of the functions being used. Conventionally, z taken as the dependent variable, like y in ordinary functions, and x and y are considered as independent variables. Thus, a function of two variables is written as z is equal to fxy. This can be denoted by an equivalent implicit equation fxyz is equal to c. It must be noted that any equation of this form may not necessarily represent a function. In microeconomics, production and utility functions are typically bivariate functions. Utility derived by a consumer depends on quantities of two goods consumed, say x and y, and production, that is the amount produced by a production unit, typically depends on the factors of production, labor and capital. Thus, utility is a function of xy and Q is a function of Lk. In macroeconomics also, income determination model and most other models involve more than one variable. The tools of multivariate functions would thus be of great help in the study of various economic problems. Example, determine the domain and range for the function z is equal to a function of xy equal to minus 5 upon y minus x. Find f at 0, 1, f at minus 2, 3 and f at 2t. The given function is defined for all xy belonging to R square except at x equal to y. That makes the denominator 0. Thus, domain D is equal to xy such that x is not equal to y. The reader may note that for each ordered pair xy in the domain F assigns a unique value to z. Further, whenever y is greater than x, F takes negative values, and for y less than x, it takes positive values. The value of f can never be 0. Range R is equal to minus infinity 0 union 0 to infinity. F01 is equal to minus 5 upon 1 minus 0, which is equal to minus 5. F minus 2, 3 is equal to minus 5 upon 3 minus 2, which is equal to minus 1. F2t is equal to minus 5 upon t minus 2. Now we will be talking about surface and level curves. Analogous to the concept of a curve in two-dimensional plane, one can talk of a surface in 3D space to graphically represent a function of two variables. Conventionally, a z-axis is drawn vertically upward and downwards perpendicular to the OXY plane. The result will be three-dimensional space, with the three axes x, y and z mutually perpendicular to each other. The coordinate z would then represent the height above or below the horizontal plane OXY for each xy belonging to D. The graph of the equation fxyz is equal to C is a locus of ordered triplets xyz satisfying the given equation. The given figure shows a surface corresponding to the equation of a plane 4x minus 2y plus z is equal to 2. Given equation can be written as z is equal to 2 minus 4x plus 2y. The points of intersection of the plane with x, y and z are respectively 1 by 2, 0, 0, 0 minus 1, 0 and 0, 0, 2. The above plane can be interpreted as a budget plane, analogous to a budget line in two dimensions, with x, y and z giving the quantities of three commodities, their coefficients being the respective prices, and the constant denoting money income of the consumer. The intercept on the axis would then give the amount of respective good purchased by spending entire income on the good in the question. Graphs in three dimensions are often difficult to draw and interpret. In particular, it is difficult to obtain quantitative results graphically. Although one can use computer graphics to draw surfaces for complicated functions, their practical utility will be limited. Of much more practical usage is what we call plane sections, corresponding to a given surface drawn in two dimensions. If a plane is passed through a surface in 3D, a curve will be traced on the plane. Such a curve is called a plane section. The plane can be principally in any direction, but of particular interest are the planes perpendicular to the three coordinate axes. The planes perpendicular to x or y axis are vertical planes parallel to z axis and are called traces or elevations, and those perpendicular to z axis are horizontal parallel to the OXY plane and are called as level curves or contours. The contour of a function fxy is thus the locus of points xy, where fxy is some constant value. It is a cross-sectional plot of the surface taken at a constant value, say z is equal to c, and projected on the OXY plane. A given function would have many level curves, one for each value of c in the range of x of fxy. A plot level curve for different values of c is called a contour plot or a contour map. Traces can be similarly drawn by taking the value of x or y as a constant and projecting the resulting curve on OYZ or OXZ plane respectively. Contour maps are commonly used in representing topographical features of Earth's surface. Such level curves are of great relevance in the production and utility theory also. The contour of production surface represents the isochords and the elevations are the respective total product curves of the factors involved. Contours of utility surface represent the indifference curves and elevations represent the total utility curve of the commodity under the concept of cardinal measurement of utility. Figure shows a contour map A and traces B for the function z is equal to xy. For equation of the contour, put z is equal to c, which implies xy is equal to c. This gives the equation of a rectangular hyperbola with asymptotes being x equal to 0 and y equal to 0. Figure A shows level curves for c equal to 0, plus minus 1, plus minus 2 and plus minus 3. Whenever c is positive, the level curves are in the first and third quadrant of the OXY plane. And when c is negative, the curve would be positioned in the second and fourth quadrants. C equal to 0 gives a rather special case. It implies either x is equal to 0 or y is equal to 0 or both x is equal to y is equal to 0. The xy axis are thus 0 contours of the function. To get the vertical plane section perpendicular to the x-axis, put x is equal to c. Then z is equal to cy. This gives straight line passing through the origin in the OYZ plane, with c being the slope of the line. Thus, c greater than 0 give upward sloping lines, c less than 0 gives downward sloping lines, and c equal to 0 give horizontal line through the origin, that is y-axis. Figure B shows the traces for c equal to 0, plus minus 1 and 2. Traces perpendicular to the y-axis will be similar lines in the OXY plane, y being kept at a constant value. An important application of a contour map is to graphically determine whether a given equation represents a function or not. If two or more contours intersect each other at a point, say x0, y0, this means that more than one value of correspondence to x0, y0. Then z will not represent a function of xy. Similarly, trace plots can be used to examine whether a given implicit relation in x, y and z represent x and y as a function of other two variables respectively. Now let us discuss limits, continuity and differentiability. The concepts of limits, continuity and differentiability extends to multivariate functions with certain modifications in the interpretation of various concepts. In one variable case, x can approach a given value a from two directions. We say that a function has a limiting value L if the function approaches L from both left hand side and right hand side, that is LSL equal to RSL as x approaches a. In case of two variable functions that are defined in R3, a given point AB can be approached from many directions. A given function fxy will have a limiting value L if whenever xy tends to AB from any direction of the function fxy tending to L. Basic rules for practically evaluating the limits of functions of two variables are those involving their scalar products, sum, difference, product and quotient remain the same as in case of single variable function. To formally define limit, the concept of neighborhood needs to be extended to R3. In a three-dimensional space, neighborhood n of a point x0 equal to AB is the interior of a ball centered at x0. N is equal to x such that modulus of x minus x0 is less than delta for some delta greater than 0. Definition of limit: a function of two variables xy is said to have a limiting value L as x tends to x0 if for every neighborhood of L, no matter how small, there exists a corresponding neighborhood of x0 in the domain of the function such that whenever x lies in the neighborhood x0, its images lie in the neighborhood of L. In other words, there exists delta greater than 0 such that modulus of x minus x0 less than delta modulus of fx minus L is less than epsilon for each epsilon greater than 0. Using the concept of limit, we can define continuity just as in the case of single variable. A function fxy will be continuous at a given point ab if fab is defined and limit of the function as xy tends to ab exists and is equal to fab. That is, limit fxy is equal to fab when xy tends to ab. A function is continuous at all points in its domain is said to be continuous over the domain. Polynomial and rational functions are continuous wherever they are defined, and various algebraic combinations, that is sum, difference, product, quotients and powers of continuous functions are continuous where they are defined. If fxy is continuous everywhere in the plane oxy, it is said to be globally continuous. Example: find the limit of fxy, which is equal to x square plus y square upon y square minus x square at the points 1, 6 and 0, 0. Also examine continuity at these points. Limit as x tends to 1b x square plus y square upon y square minus x square is equal to 1 square plus 6 square upon 6 square minus 1 square, which is equal to 1 plus 36 upon 36 minus 1, which is equal to 37 upon 35. It will not be possible to evaluate limit as xy tends to 0, 0 in the same way because f0, 0 is not defined. So limits are evaluated separately along the x and y axis. As xy tends to 0, 0 along x axis, that is y is equal to 0. fx0 is equal to x square plus 0 upon 0 minus x square, which is equal to minus 1. That is, fxy tends to minus 1 as xy tends to 0, 1 along the x-axis. Similarly, as xy tends to 0, 0 along y-axis, then f0y is equal to 0 plus y square upon y square minus 0 is equal to 1. Since the limits along x and y axis are different, that is, limit xy tending to 0, 0 x square plus y square upon y square minus x square does not exist. For continuity at 1, 6, note that, therefore, the given function is continuous at 1b. At 0, 0, limit of the function does not exist, so the function is discontinuous at 0, 0. This continuity is irremovable. Note that the given function is not defined for xy equal to plus minus y. So it will be discontinuous along x equal to y and x equal to minus y. The reader may verify by evaluating the limits for various points on these lines separately along the x and y axis. that the function exhibits an infinite discontinuity along these lines. Continuity is a necessary but not a sufficient condition for differentiability, just as in the case of one variable functions. If both the first order partial derivatives exist and are continuous in a neighborhood of the point xy equal to ab, then f is differentiable at ab. If both partial exist and are continuous over the domain of the function, we say that f is continuously differentiable and write C1 for the function. If all partial derivatives up to order k exist and are continuous, we write the function as Ck. We will now look at the functions of more than two variables. The concept of a function of two variables can be easily generalized to any number of variables. A function f of n variable, say x1, x2 till xn, with domain D is a rule that assigns a unique real number f x1, x2 till xn to each point x1, x2 till xn belonging to D. Domain D is equal to x1, x2 till xn such that f x1, x2 till xn belongs to R, and range is the set of all f values. We can write z is equal to f x1, x2 till xn. Demand and supply for a commodity in economics typically depend on a number of factors. For instance, demand depends on own price, price of other related goods, income level of the consumer, taste preferences, etc. Supply depends on own price, price of inputs, goal of the producer, state of technology, etc. dx is equal to f px, p1, p2 till y. Sx is equal to g px, f1, f2 till gt. In economics, domain is often restricted to positive values of the variables for most economic variables. Negative values make no sense. Domain and range of multivariate functions in general can be found just as in the case of bivariate functions. The graph of such function is often called a hypersurface, although no concrete geometric representation is feasible once we move beyond 3 dimensions. Plane sections can be drawn by keeping one variable constant. Plane sections perpendicular to the z-axis are often called by the name level surface. The concept of limits, continuity, and differentiability extend in the same way as for two variables.
To summarize, a set S defined over vector space Rn is said to be convex if for any 2 points belonging to the set, the line joining those points also belongs to that set. A set S in Rn is convex if P belongs to S, Q belongs to S, and lambda is in between 0 and 1 such that 1 minus lambda P plus lambda Q belongs to S. A function f of two variables, say x and y, with domain D is a rule that assigns a unique real number fxy to each point xy belonging to D. Domain D is equal to xy such that fxy belongs to R, and range is the set of all those f values. A surface in the 3D space graphically represents a function of two variables. If a plane is passed through a surface in 3D, a curve will be traced on the plane. Such a curve drawn in 2D is called as a plane section. Equation of vertical plane section or contour is obtained by putting fxy equal to c, and similarly for other plane sections. The concepts of limit, continuity, and differentiability extend to multivariate function with certain modifications in the interpretations of various concepts.